If the ancestral population of anatomically modern humans had succumbed to a localized extinction event 300,000 years ago, our planet would look vastly different today. Instead, the Earth would have been inherited by a highly diverse, multipolar system of deeply specialized archaic hominins. Without us monopolizing the globe, the evolutionary landscape would belong to a triumvirate of distinct species. The cold-adapted Neanderthals would dominate the west, while the high-altitude Denisovans held the east, and the insular dwarf Homo floresiensis navigated the southern archipelagos. These societies demonstrate that technological development and ergonomic design function as strict mechanical interfaces dictated by cranial morphometrics. Let's compare a modern Homo sapiens skull to a bicycle helmet. We possess a globular parietal curve, a tall vertical forehead to grip the front of a hat, and a protruding bony chin to act as a secure anchor for straps. A modern bicycle helmet or a baseball cap would fail on one of our archaic cousins. Their long, backward-sloping foreheads would cause the gear to slide off the back, while standard straps would slip down their chinless jaws and choke them. To accurately reconstruct these archaic civilizations, we must treat their material culture, specifically their headwear, as a rigorous biomechanical problem constrained by bone and genetics. The Neanderthal lineage evolved in the freezing, low-light periglacial zones of Pleistocene Europe. Surviving in this dim environment required enlarged orbits and a massive visual cortex to capture light, an adaptation that sacrificed prefrontal real estate. This hyper-developed visual processing system created a biological imperative for heavy structural facial shading, as a Neanderthal on glaring glacial ice would suffer from extreme photophobia or light sensitivity. This creates a biomechanical paradox. They required a heavy front visor to block the sun, yet that visor could not rest flat on a receding forehead, and the lack of a protruding chin eliminated standard strapping solutions. This technical diagram identifies the solution at the back of the Neanderthal skull, the occipital bun. It functions as a posterior mechanical cleat. Their headwear utilized a specialized rear pocket cupping this bony protrusion to counterweight the heavy visual visor in the front. Neanderthal headwear utilized synthetic birch pitch and advanced leatherworking to engineer a counterweighted, armored extension of their robust anatomy. In the east, the Denisovans held a vast hegemony across the Tibetan Plateau and Asian steppes. They survived extreme cold, severe ultraviolet radiation, and atmospheric hypoxia, which is a state of low oxygen levels. Their mastery over this environment was genetic. They possessed a variant of the EPAS1 gene, which suppresses the dangerous overproduction of red blood cells, allowing them to extract oxygen efficiently at altitudes that would kill other species. The Denisovan skull, exemplified by the Harbin cranium, features a wide face, a flat nasal saddle, and nearly parallel lateral walls with no outward expansion. This wide, flat skeletal architecture demands broad-spectrum shielding. Denisovan headwear functioned like a rigid, high-altitude parasol, casting a permanent shadow over their broad shoulders. This diagram shows how they secured wide structures to a receding jaw. Denisovan mastoid processes, bones behind the ears, are large and incline inward. By utilizing an inward mastoid grip, rigid flaps clamp securely behind the ears, locking the brim down without a throat strap. By leveraging unique skeletal geometry to anchor thermal and radiation shielding, the Denisovans monopolized the planet's most extreme elevations. In the isolated, calorie-starved archipelagos of Sundaland, Homo floresiensis adapted through insular dwarfism, shrinking to roughly 3.5 feet tall. Despite having a 420 cubic centimeter microbrain, roughly the size of a chimpanzee's, their highly derived prefrontal cortex permitted complex cognitive and symbolic thought. We see their profound physical vulnerability through finite element analysis. A heat map overlays the temporal mandibular joint, connecting the jaw to the skull. Heavy biting produces severe tensile reaction forces here. Chewing tough materials creates a high risk of complete jaw dislocation. This biomechanical fragility makes them obligate tool users. They physically cannot survive without slicing tools and fire for pre-oral food processing. Their reliance on highly active, cooperative hunting strategies against massive island megafauna meant their headwear had to remain firmly attached during erratic, violent movement. The right panel reveals the unique harnessing system required for a species lacking a chin. They utilized a submandibular web. This wide netting of woven fibers distributes tension across the jawbone's underside, securely anchoring their fitted microdome far back on a receding forehead. Floresian technology is a delicate, highly efficient material culture woven from plant fibers that perfectly compensates for their severe biomechanical limitations. These three distinct material cultures map directly onto their global geopolitical territories: the European steppes, the high-altitude Asian interior, and the oceanic archipelagos. These species operated on a stable, highly specialized model of innovation, resembling an extended Iron Age, avoiding the rapid technological disruption driven by Homo sapiens. Because large portions of their neural real estate were dedicated to visual processing and somatic maintenance, their Dunbar numbers, the cognitive limit on social group size, would naturally cap the scale of their societies. They would likely form decentralized guild states rather than trust-based megacities. As these populations expanded, border clashes and geopolitical volatility would occur, particularly during multi-species migrations across the Bering Land Bridge into the Americas. In this alternate reality, hard genetic constraints and biological tolerances to extreme environments dictate the boundaries of global imperial power. Complex intelligence and globe-spanning civilization do not require the specific globular biological chassis of modern humans. Radically different neural architectures, ranging from 1,500 cubic centimeter elongated vaults to 420 cubic centimeter microbrains, can all arrive at advanced ecological engineering. As this diagram illustrates, the exact same functional problem, securing protective headwear, was elegantly solved three entirely different ways using an occipital bun, inward inclining mastoid processes, and a submandibular web. Advanced civilization functions as a biological attractor, capable of emerging through myriad, divergent, and highly resilient anatomical forms.